The first image did not look like a doorway. It looked like a blurred ring of radio light, orange in the public version, brighter on one side, with a dark center where the radiations seemed to fall away. On the screens of the Event Horizon Telescope collaboration, it was not a photograph in the ordinary sense. It was a reconstruction from radio dishes scattered across Earth, from atomic clocks, hard drives, algorithms, weather logs, calibration checks, and a signal so faint that the planet itself had to become part of the instrument. At the center of that ring was the black hole in Messier 87, a giant galaxy in the Virgo cluster. Its mass is measured in billions of suns. Its distance is measured in tens of millions of light years. The light surrounding it began its journey before human beings existed, before our species made tools, before the continents and climates of the present world had taken their familiar shapes. By the time that light reached Earth, astronomers had learned to combine radio telescopes into a virtual dish almost as wide as the planet. The image did not show the event horizon directly. Nothing can. What it showed was the region around it, where hot plasma moved through warped space-time, where light bent around the black hole before escaping toward Earth, and where the interior of the ring was dim because light paths near the hole were being swallowed or redirected. It was not a picture of a surface. It was a picture of gravity shaping visibility. That is the difficulty with black holes. They are among the most famous objects in astronomy, but they are known mostly by what happens around them. We see the star pulled into a distorted orbit. We see an accretion disk glowing in X-rays. We see a jet thrown outward across thousands of light years. We see gravitational waves when two dark objects spiral together and merge. We measure the absence, but the absence is not empty. It has mass, spin, temperature, geometry, and consequences. Beyond the event horizon, the problem becomes sharper. The boundary is not a wall. It is not a shell of material waiting to be struck. It is a region in spacetime where all possible paths forward, even the paths taken by light, lead inward. For an observer far away, that boundary marks the point after which no message can return. For something falling in, the crossing may not be locally dramatic, especially if the black hole is large enough. The danger is not always at the edge. The deeper danger lies in the future that the horizon makes unavoidable. If the quiet questions at the edge of physics are what bring you here, subscribing keeps the next long journey close. The phrase black hole can make the object sound like a place where matter simply disappears. That is not quite right. From the outside, mass does not vanish. It remains present in the curvature of spacetime, in the orbital motion of stars, in the path of light, in the timing of signals, and in the way surrounding matter heats as it falls. A black hole can be weighed. Its spin can be constrained. Its influence can be mapped. The part that cannot be directly observed is the interior, and that is where the title becomes difficult. The event horizon is a boundary of information. It is defined by escape, not by hardness. If you hover outside it, with an engine powerful enough, you can still send a radio signal home. If you cross it, no engine, mirror, rocket, or beam of light can make a message reach the universe outside. This is not because the signal is too weak in an ordinary sense. It is because the geometry of spacetime no longer provides an outward route. To understand what really happens beyond that boundary, we have to separate three different stories that often get mixed together. There is the story seen by a distant observer watching something fall in. There is the story experienced by the falling object itself. And there is the mathematical story told by general relativity once the horizon has been crossed. These stories do not contradict each other, but they describe the same event from different positions in spacetime. From far away, an object approaching the horizon appears to slow down. Its light becomes stretched to longer wavelengths. The signal grows fainter. Each successive pulse takes longer to arrive. In the most literal description from that distant coordinate system, the object never quite appears to cross. It becomes redder, dimmer, and harder to detect until it effectively fades from the observable world. This is not how the falling object experiences the passage. For the falling object, time continues locally. A clock carried inward ticks normally beside the hand holding it. The horizon, if the black hole is enormous, may not announce itself through any sudden impact. There is no glowing line painted across space. There may be no violent jolt at the exact moment of crossing. The object simply passes from a region where escape is possible into a region where escape is not, while its own immediate surroundings may still seem ordinary over a small enough scale. The difference comes from the nature of relativity. Time is not universal, and gravitational fields do not only pull on matter. They shape how clocks tick, how distances are measured, and how light travels. Near a black hole, the difference between local experience and distant observation becomes extreme. What looks frozen from outside can be finite for the one falling in. What looks like a boundary in a diagram may feel, at first, like continuing forward through space. That calm does not last forever. The same gravity that creates the horizon also creates tidal forces, differences in gravitational pull from one part of an object to another. Near a small stellar mass black hole, the difference between the pull on your feet and the pull on your head could become lethal before you reach the horizon. Near a supermassive black hole, the horizon can be so large that those tidal differences at the boundary are comparatively gentle. You could cross before the stretching became destructive. This is why the size of the black hole matters. A stellar black hole formed from a collapsed massive star may have an event horizon only tens of kilometers across. A supermassive black hole in a galactic center may have a horizon larger than the orbit of planets. The gravity at the horizon is not the same in every case. The smaller black hole has stronger tidal gradients at its edge. The larger one can hide its most violent changes deeper inside. The word spaghettification sounds almost too casual for what it describes. It is the stretching of matter along the direction of gravity and the compression of matter across the sideways directions. A falling body becomes a long, thinning stream because the nearer side is pulled more strongly than the farther side. Stars can be torn this way when they pass too close to a supermassive black hole, producing tidal disruption events that flare across optical, ultraviolet, and X-ray surveys. For a human body, for a spacecraft, for a planet, the underlying physics is the same. Different parts of the object are no longer allowed to behave as a single rigid system. Gravity does not pull every part equally. Materials stretch, heat, break, and eventually become part of an inward moving flow. In realistic astrophysical situations, radiation, magnetic fields, collisions, and plasma turbulence may complicate the scene long before any clean textbook picture appears. The simplest black hole in equations is quiet, isolated, non-rotating, and perfectly spherical. Real black holes are not usually like that. They rotate. They are surrounded by gas, stars, magnetic fields, and sometimes other compact objects. Their environments can be messy, bright, and violent. But the event horizon remains the central idea. It is the boundary beyond which the future of a falling object no longer includes the outside universe. A black hole does not need to be fed in order to exist. A quiet black hole in empty space would be almost invisible, detectable only through its gravity, through lensing, or through the motion of something nearby. The dramatic images of glowing disks and jets come from matter outside the horizon. That matter has not yet crossed. It is being heated, twisted, shocked, and magnetized while it still belongs to the observable universe. An accretion disk forms when matter falls toward a black hole with angular momentum. Instead of dropping straight in, gas settles into orbit, shears against itself, and loses energy through friction and magnetic turbulence. The disk becomes hot. Around stellar mass black holes, it can glow in X-rays. Around supermassive black holes, it can help power quasars so bright that a galaxy's center outshines the stars around it. The brightness is not the black hole itself. It is matter giving up gravitational energy before crossing the boundary. Some of the most powerful structures in astronomy are connected to this process. Jets of charged particles can be launched from the regions around spinning black holes, guided by magnetic fields, and fed by the energy of rotating plasma, and possibly by the spin of the black hole itself. These jets can pierce their host galaxies and extend far into intergalactic space. They do not come from inside the horizon. Once matter is inside, it cannot return. The launching has to happen outside, in the region where fields and particles can still communicate with the wider universe. The event horizon, then, is not where all the visible action happens. It is where visibility ends. Outside it, gas can glow, collide, orbit, and emit. Light can skim the curved geometry and escape after looping around. Magnetic fields can carry energy outward. Inside it, every future-directed path points deeper inward. The outside universe becomes something that cannot be reached, no matter how much fuel, force, or intention is applied. This is the part of black hole physics that feels least intuitive, because it is not simply a stronger version of ordinary falling. On Earth, falling means moving through space toward the ground. Inside a black hole, according to general relativity, moving inward is woven into the future itself. The singularity is not just a place ahead in space. It becomes something more like a moment that every possible future path must meet. Diagrams of black holes often show a funnel in a sheet, with a marble rolling inward. That image helps explain curvature, but it can also mislead. The real curvature is not a dip in space embedded in a higher room. It is the curvature of space-time itself. The event horizon is not a rim, it is a light-trapping boundary in four-dimensional geometry. The mathematics is precise, but translating it into images always leaves something out. A falling astronaut would still be surrounded by local physics. Small objects nearby would drift according to their own trajectories. A flashlight could still send light across the cabin. A clock would still tick. The equivalence principle, one of the foundations of general relativity, says that over a small enough region, free fall can feel like weightlessness. The horizon is global. It depends on whether light can ultimately escape to infinity, not only on what a falling observer feels at one point. That distinction is why the horizon can be crossed without a flash or a crack in space. If the black hole is large and the surroundings are not filled with lethal radiation, the crossing itself could be locally subtle. The equations do not predict a solid membrane there for ordinary classical relativity. The catastrophe comes later, from the convergence of paths and the growth of tidal forces as the interior geometry carries matter toward the central region. The word later also needs care. Inside the horizon, time and space are not interchangeable in a casual way, but the coordinates that describe the outside no longer behave as they did. The radial direction becomes unavoidable in a way that resembles the forward movement of time. You can move your arms, fire a rocket, aim a beam, and still all future paths move toward smaller radius. The problem is not insufficient speed. It is that the outward direction has left the set of possible futures. For a non-rotating black hole, classical general relativity predicts that the interior ends at a singularity, where curvature grows without limit and the theory itself reaches a boundary. This is often described as a point of infinite density, but the phrase can be too simple. What matters physically is that the equations signal their own breakdown. Measurements that describe curvature and tidal gravity become unbounded. The theory that predicted the black hole also tells us that something about the prediction is incomplete. Physicists do not take the singularity as an ordinary object sitting at the center like a dense stone. A singularity is a sign that the mathematical description has reached a place where it can no longer give a complete physical account. General relativity has been tested with extraordinary success in weak and strong gravitational fields, from planetary orbits to gravitational waves. But near the singularity, quantum effects should matter, and we do not yet have a complete Experimentally confirmed theory of quantum gravity. This is where honest uncertainty enters. We can describe the horizon with confidence in the framework of general relativity. We can observe the outside consequences of black holes with telescopes and detectors. We can model accretion disks and mergers with numerical simulations. But the deepest interior is not accessible to direct observation. No probe can cross and report back. No telescope can look through the boundary. The interior is known through theory, not through returned data. The question, what really happens beyond the event horizon, therefore has two answers. One answer comes from the best classical theory of gravity, which says that crossing the horizon is locally ordinary for a large black hole, and that the future leads inevitably toward a singularity. The other answer comes from the incompleteness of current physics, which says that near the final region, general relativity should give way to a deeper theory that has not yet been confirmed. Black holes became real to astronomy slowly. They were first mathematical possibilities, then candidates in X-ray binaries, then massive compact objects inferred from stellar orbits, then sources of gravitational waves, then shadows reconstructed by radio interferometry. The path from equation to evidence took more than a century. It passed through skepticism, better instruments, cleaner measurements, and the patient accumulation of things that ordinary stars or clusters could not explain. The compact radio source at the center of the Milky Way, Sagittarius A star, became one of the strongest examples. Astronomers watched stars orbiting an unseen mass near the galactic center. Some stars passed close enough and fast enough that their orbits revealed millions of solar masses contained in a region too small to be an ordinary cluster of dark stars. Infrared telescopes cut through dust. Adaptive optics sharpened the measurements. Year after year, the paths of those stars drew the gravitational field. Those observations did not require anyone to see the horizon itself. Gravity wrote the evidence into the motion of stars. A compact object with roughly 4 million solar masses sits at the center of our galaxy, about 26,000 light-years away. Its behavior, size constraints, and mass make a black hole the best explanation. The ET later imaged the ring of emission around Sagittarius A star as well. More difficult than M87 because the source changes quickly on human observing timescales. M87 offered a different kind of target. Its central black hole is far more massive, which means changes near its horizon unfold more slowly from our point of view. Though it is much farther away than Sagittarius A star, its event horizon scale structure appears large enough on the sky for the Event Horizon Telescope to resolve. The reconstructed ring was a test of whether the size and shape matched the predictions of general relativity for a black hole shadow. The word shadow can also mislead if taken too literally. It is not a shadow cast on a wall, it is a dark depression in brightness caused by light paths near the black hole. Some photons orbit briefly before escaping. Some fall inward. Some originate from hot plasma behind the black hole and are bent around it. The result is a ring-like structure whose diameter depends on the mass, distance, and space-time geometry. The ring in the M87 image is not the event horizon itself, but it is tied to the region where gravity dominates light. That is why it mattered. For the first time, the scale of a black hole predicted from stellar and gas dynamics could be compared with horizon-scale radio emission. The result was not a perfect, simple photograph. It was better than that scientifically. It was a measurement built from many independent checks. Long before the first image, black holes had already been detected through another messenger. In September 2015, the LIGO detectors recorded a passing gravitational wave from two stellar mass black holes merging far away. The signal lasted a fraction of a second in the most sensitive band, rising in frequency and amplitude as the objects spiraled together. It was a sound-like trace made from space-time strain, not from air. The detectors measured changes smaller than a proton across kilometer-scale arms. That first detection confirmed that black holes can exist in pairs, orbit each other, lose energy through gravitational waves, and merge into a larger black hole. The final object rang down, settling into a stable form described by mass and spin. In that ringing, physicists could compare the signal with the predictions of general relativity. The event horizon was not imaged, but the merger behaved like the collision of objects that had no hard surfaces. Gravitational waves are especially important because they come from the motion of space-time itself. Light can be blocked, scattered, absorbed, or delayed by matter. Gravitational waves pass through the universe with very little obstruction. When black holes merge, the strongest waves are produced in the last moments before and after the horizons combine. The signal does not reveal the interior directly, but it probes the exterior geometry with a clarity that ordinary telescopes cannot provide. In a merger, the horizons do not crash like metal spheres. The geometry changes. Two trapped regions become one. Numerical relativity, solved on supercomputers, follows the equations through the violent final orbits and ringdown. These simulations were essential before the detections arrived because the measured signal had to be compared with predicted waveforms. Without the models, the chirp would have been a strange disturbance in the detectors. With them, it became a cosmic event with masses, distance, and spin. The horizon hides the interior, but it does not hide the black hole's external properties. According to the classical no-hair idea, a settled black hole can be described by only a few quantities: mass, electric charge, and angular momentum. Astrophysical black holes are expected to have negligible net charge, leaving mass and spin as the practical parameters. This simplicity is part of what makes black holes powerful laboratories. Enormous complexity falls in. The exterior settles into a remarkably simple gravitational field. That simplicity is also part of the information problem. If matter with detailed structure collapses into a black hole, and if the black hole eventually evaporates through Hawking radiation, what happens to the information that described the original state? Quantum mechanics says information should not simply be destroyed. Classical black hole physics seems to hide it behind a horizon. Hawking radiation introduced a deeper tension, because the radiation appears thermal in the simplest treatment. Hawking radiation is not important for the daily behavior of astrophysical black holes. For a black hole with the mass of a star, the temperature is far colder than the cosmic microwave background, and the evaporation time is vastly longer than the current age of the universe. But conceptually, it matters enormously. It connects gravity, quantum fields, thermodynamics, and information. It suggests that black holes are not entirely black forever, even if the radiation is far too weak to detect from known stellar or supermassive black holes. The information paradox remains one of the major clues that our understanding is incomplete. Many ideas have been proposed: holography, complementarity, remnants, firewalls, fuzzballs, subtle correlations in radiation, and other approaches from quantum gravity. Some have strong mathematical support in particular settings. None has yet become a directly tested description of real astrophysical black hole interiors. The paradox is not a license to invent anything. It is a signpost pointing to physics that is still unfinished. The event horizon sits at the center of this tension because it separates what can be observed from what cannot. In ordinary science, inaccessible regions can still be studied indirectly. We infer the cores of stars from light, neutrinos, and oscillations. We infer exoplanets from tiny dips and stellar wobbles. We infer dark matter from gravity. But a black hole horizon is stricter. It allows influence outward through mass and spin already present, but it does not allow new messages from inside to return. This does not mean the interior is meaningless. It means our statements about it must be tied to theory. General relativity gives a clear classical account. Quantum theory demands caution near the final state. Observations outside the horizon test the framework around it. The closer those observations get to horizon scales, the more pressure they place on speculative ideas. A theory of black holes must explain not only strange interiors, but also the very ordinary accuracy of the exterior predictions. A black hole formed from a massive star begins before the horizon exists. The star spends millions of years balancing gravity against pressure from nuclear fusion. Hydrogen fuses into helium. Later stages build heavier elements in shells around the core. When the fuel that can support the core runs out, gravity wins. For some stars, the collapse leaves a neutron star. For others, the core is too massive, and no known pressure can stop the inward fall. During collapse, the event horizon forms around a region from which light can no longer escape. To distant observers, the surface of the collapsing star appears to slow and dim as it approaches the horizon. In the star's own falling frame, matter continues inward. The formation of a black hole is not matter passing through a pre-existing hole. It is space-time itself developing a trapped region because enough mass has been compressed into a small enough volume. The threshold for forming a black hole is often described with the Schwarzschild radius. Compress the sun into a sphere only a few kilometers across, and it would become a black hole. Earth would have to be compressed to a size of roughly a centimeter. These comparisons are useful, but they do not mean ordinary objects are in danger of suddenly becoming black holes. The required compression is extreme. Black holes form in the universe through gravitational collapse, mergers, and possibly early universe processes that remain under investigation. Once formed, a black hole can grow by accretion or by merging. Gas falling in can radiate enormous energy before it crosses the horizon. Another black hole can spiral inward and combine. In galactic centers, repeated growth across cosmic time may produce supermassive black holes with millions or billions of solar masses. The details of how the earliest massive black holes grew so quickly remain an active area of research, especially as infrared telescopes find bright quasars in the young universe. A quasar is not a black hole shining by itself. It is a feeding supermassive black hole surrounded by an accretion flow so luminous that it can be seen across much of the observable universe. The light comes from gas outside the horizon. Matter falling inward loses gravitational energy, heats to extreme temperatures, and radiates before it disappears. Some quasars are seen as they were when the universe was less than 1 billion years old, making them clues to early structure formation. The existence of very distant quasars raises questions about seed black holes. Did they begin as remnants of the first massive stars? Did some form through direct collapse of gas clouds? Did dense star clusters produce runaway mergers? Current observations and simulations explore all of these possibilities. The event horizon remains the same kind of boundary, but the cosmic history around it changes. A black hole in the early universe is not only an object, it is a clue to how galaxies assembled. Inside a stellar collapse, beyond the forming horizon, the matter's future narrows. In the classical picture, pressure cannot halt the collapse once the trapped region has formed. The inward direction becomes inevitable. The collapsing material continues toward a singularity, but this is also where density, curvature, and quantum effects move beyond conditions we can reproduce in laboratories. The final interior state is predicted by equations that we know are incomplete at extreme scales. A rotating black hole complicates the picture. Real stars rotate, and the collapsed objects they leave behind are expected to rotate as well. The rotating solution in general relativity is called the Kerr black hole. Instead of a perfectly spherical, static spacetime, it has frame dragging, an ergosphere, and a different internal structure. Outside the horizon, frame dragging means spacetime is pulled around with the black hole's rotation, forcing objects near it to share some of that motion. The ergosphere is not the event horizon. It is a region outside the horizon where remaining still relative to distant stars becomes impossible. Energy can, in principle, be extracted from a rotating black hole through processes involving the ergosphere. Astrophysical jets may also draw on rotational energy through magnetic fields connected to plasma outside the horizon. These ideas are studied through theory, simulations, and observations of active galaxies, but the details are difficult because the plasma physics is complex. Crossing the horizon of a rotating black hole still means no return to the outside. But the interior of the mathematical Kerr solution includes features unlike the simple non-rotating case, including an inner horizon and a ring-like singularity in the idealized equations. Scientists treat these features carefully. Realistic perturbations, infalling radiation, and quantum effects may change the interior dramatically. The exact internal structure of a real rotating black hole is not something observations have settled. This is an important restraint. It is tempting to turn the Kerr interior into a tunnel, a passage, or a route to another region of spacetime. Some mathematical extensions allow strange possibilities on paper, but an equation extended beyond its stable physical regime is not the same as an astrophysical object offering passage. The interiors of rotating black holes are active research territory, not confirmed doorways. The evidence we have supports black holes as compact objects with horizons, not science fiction corridors. For someone falling into a rotating supermassive black hole, the local journey could differ from the simplest model, but the basic information boundary remains. Before crossing, light can still be sent outward if the path is possible. After crossing, every future path stays inside. Tidal forces grow. Radiation from the surrounding environment may be deadly if the black hole is actively feeding. The details depend on mass, spin, accretion state, and trajectory. There is no single universal fall that covers every black hole. Near an active black hole, the environment outside the horizon may be more dangerous than the crossing itself. The accretion disk can be intensely hot. Particles move at large fractions of the speed of light. Magnetic fields twist through plasma. X-rays and gamma rays can flood the region. A traveler would not approach through clean darkness. They would pass through a physical environment shaped by heat, radiation, and high-speed matter, unless the black hole were unusually quiet. Sagittarius A star is quiet compared with many active galactic nuclei. It has material around it, but it consumes only a small fraction of what is available. X-ray flares show that its environment changes. Infrared observations reveal stars moving through the central region. Radio images probe the plasma close to the hole. It is not dormant in an absolute sense. It is faint relative to what a 4 million solar mass black hole could be if it were being fed heavily. M87's black hole is different. It powers a prominent jet visible across wavelengths, from radio to optical to X-rays. The jet extends far beyond the central ring, imaged by the EAT. That means the black hole's influence is not confined to the horizon. Through accretion and magnetic fields, it affects gas across galactic scales. Energy released near the center can heat surrounding material and influence how stars form or fail to form in the galaxy. This feedback is one reason supermassive black holes matter to galaxy evolution. Galaxies are not just collections of stars. They contain gas, dust, dark matter, magnetic fields, cosmic rays, and central black holes. When a black hole feeds strongly, the energy released outside its horizon can push on gas or heat it. Over time, this can regulate star formation. The black hole is small compared with the galaxy, but the energy around it can be large enough to shape the larger system. The Milky Way's central black hole is not currently a quasar, but evidence suggests that galactic centers can change over time. Gas clouds fall in. Stars pass close. Accretion rates rise and fall. A black hole can spend long periods in a quiet state, then briefly flare when material becomes available. The horizon does not change its basic nature, but the observable face of the black hole depends heavily on its surroundings. This is why black holes should not be imagined only as cosmic drains. Most matter in a galaxy will never fall into the central black hole. Stars orbit the galactic center because of the combined gravity of the galaxy, not because the black hole is vacuuming everything inward. If the Sun were replaced by a black hole of the same mass, Earth would continue orbiting almost as before, though without sunlight the planet would become uninhabitable. Gravity depends on mass and distance, not on the word black hole. The event horizon is dangerous because of where it is, not because it reaches out with special suction. Far from a black hole, its gravity behaves like the gravity of any object with the same mass. Close to it, the compactness matters. The mass is concentrated inside a region so small that escape paths vanish. That compactness is what creates the horizon and the strong tidal fields near smaller black holes. Astronomers search for black holes by looking for compactness. In X-ray binaries, an unseen object pulls gas from a companion star. The gas forms a disk and emits X-rays. If the compact object is too massive to be a neutron star, and if other evidence fits, it becomes a black hole candidate. In galactic centers, stellar or gas orbits reveal mass packed into tiny volumes. In mergers, gravitational waves reveal the masses and dynamics of horizons joining. There are also black holes that may be detected by microlensing. A dark, compact object passing in front of a distant star can magnify the star's light through gravity. If no luminous lens is seen and the inferred mass is high enough, a black hole becomes a possible explanation. These detections are challenging because the lens may be a faint star, a neutron star, or another compact object. The measurement is indirect, as many astronomical measurements are. Indirect does not mean weak. Much of astronomy is indirect because most objects cannot be touched. We know stars by their spectra. We know exoplanets by dimming curves and stellar wobbles. We know galaxy masses by rotation, lensing, and motion. Black holes are part of this larger pattern. They are inferred from how matter, light, and space-time behave. Their strongest evidence comes when different methods point to the same conclusion. Beyond the event horizon, however, the usual indirect paths become limited. No spectrum emerges from inside. No orbit can be tracked after crossing. No probe can send telemetry back. The interior is not like the far side of the moon before spacecraft, hidden but reachable. It is hidden by causal structure. That makes black holes different from ordinary remote places. They are not merely distant. They are one-way regions in the fabric of spacetime. A useful way to imagine the crossing is to think about light cones. At any event in spacetime, the future light cone represents the directions light can travel from there. Far from a black hole, some future directions lead outward, some inward, some sideways. Near the horizon, the cone's tip. At the horizon, the outward edge just fails to escape. Inside, the entire future cone points towards smaller radius. Even light aimed outward moves deeper in the only future available. This does not mean light stops moving locally. A beam inside the horizon still travels at the speed of light relative to a nearby observer. The issue is not local speed, it is the global geometry of where future directed light paths go. The beam can move across a cabin, reflect from a mirror, or pass a nearby object. But no arrangement makes it climb back to infinity. The outside universe is no longer in its future. For a falling observer, looking outward after crossing raises subtle questions. Light from the outside can still enter the horizon after them, so the outside universe may remain visible in distorted ways for some time. But sending a message outward is impossible. The view would be affected by motion, gravity, the black hole's environment, and the observer's trajectory. Popular images of watching the entire future of the universe flash by are oversimplified. The real calculation depends on the spacetime and path. The interior of a large black hole can be physically vast. The horizon radius of a supermassive black hole can span millions or billions of kilometers. Crossing it would not place the falling observer immediately at the final destructive region. There could be finite time between crossing and reaching the singularity, more for larger black holes. But finite is the crucial word. In the classical picture, There is no permanent station inside. Every route continues inward. Firing rockets after crossing cannot solve the problem. A rocket can change the path and may alter how much proper time remains before encountering the central region, but it cannot create an outward future. In some cases, firing in what feels like the outward direction may even reduce the remaining time, depending on the trajectory. Inside the horizon, intuition built from ordinary space becomes unreliable. The equations, not instinct, decide what paths exist. Matter falling into an accreting black hole may not cross as intact objects. Gas is stretched into streams, collides with other gas, heats, and becomes plasma. Magnetic fields transport angular momentum outward, allowing material to move inward. Turbulence makes the disk time variable. Before any particle crosses the horizon, it may have been part of a star, a cloud, a disk, a flare, and a spiral of radiation. The journey inward is often not clean. In tidal disruption events, a star passing too close to a supermassive black hole is torn apart outside the horizon. Roughly speaking, some of the stellar material is flung outward while some remains bound and falls back, forming a temporary accretion flow. Telescopes see a flare that rises and fades over weeks, months, or longer. These events give astronomers a way to study otherwise quiet black holes, because the star briefly lights the environment around the horizon. The star does not vanish all at once. It is converted into a stream of gas by tidal forces. Parts of the stream collide and shock. Radiation emerges from the newly heated material. The black hole gains only the matter that actually crosses the horizon. The rest can remain in orbit or escape. Even in destruction, the process is governed by gravity, energy, angular momentum, and radiative physics, not by a simple swallowing motion. On smaller scales, a stellar mass black hole in a binary can strip gas from its companion for millions of years. The disk brightens and dims. Outbursts occur when the flow changes state. Jets may appear in radio observations. X-ray satellites track the inner disk. These systems are laboratories because they evolve quickly enough for humans to watch changes over days and years, unlike many supermassive black holes whose timescales can be longer. The inner edge of an accretion disk is related to the black hole's spacetime. Around a non-rotating black hole, there is an innermost stable circular orbit. Inside that radius, stable circular orbits are no longer possible, and matter plunges inward. For a rotating black hole, the location depends on spin and direction of orbit. Measuring disk emission and reflection features can help estimate spin, though the method depends on models and assumptions about the disk. Spin matters because it stores rotational energy. A rapidly rotating black hole drags spacetime more strongly. Magnetic fields threading the surrounding plasma can, under the right conditions, extract energy and help power jets. Observations of jets and disks do not give a simple spin meter in every case, but they show that black holes are not only masses, they are rotating gravitational systems embedded in astrophysical environments. Inside the horizon, the role of spin becomes harder to turn into a simple narrative. The mathematical Kerr solution has regions that differ from the Schwarzschild interior. But real black holes are formed by collapse, disturbed by infalling matter, and surrounded by radiation. Inner horizons may be unstable. The singularity may not resemble the idealized solution once perturbations and quantum effects are included. Serious physics does not require pretending the ideal diagram is a travel map. The safest statement is this: general relativity predicts that once the horizon is crossed, escape is impossible, and the falling object's future reaches a region where classical curvature becomes extreme. For a non-rotating black hole, that endpoint is the space-like singularity. For rotating black holes, the ideal mathematical structure is more complicated, but it is not observationally confirmed as a navigable interior. Near the deepest region, we expect the classical description to fail. The failure of a theory at an extreme is not a weakness in the ordinary sense. Newtonian gravity fails near black holes, but it remains excellent for many solar system calculations. General relativity may fail near singularities while remaining the best-tested theory of gravity across a huge range of conditions. A deeper theory should reproduce general relativity where it works and modify it where it does not. That is a difficult demand. Quantum gravity is not one theory with one confirmed answer. String theory, loop quantum gravity, asymptotic safety, causal sets, holographic approaches, and other programs explore different paths. Some propose that singularities are resolved. Some suggest the interior is replaced by quantum structure. Some emphasize that information is encoded holographically. These ideas are mathematically serious in different ways, but the universe has not yet provided the decisive observation that chooses among them. The event horizon may also be tied to black hole thermodynamics. Black holes have entropy proportional to horizon area, not volume. This is a strange and important result. Entropy usually counts the number of microscopic states compatible with a macroscopic description. For black holes, the area law hints that the information content of a region may be related to its boundary. This insight helped lead to holographic ideas in theoretical physics. Temperature enters through Hawking radiation. In quantum field theory on curved spacetime, black holes emit radiation with a temperature inversely related to mass. Smaller black holes are hotter. Large astrophysical black holes are extremely cold. If a black hole could be isolated from the cosmic microwave background and wait for unimaginable spans of time, it would lose mass through this radiation. But for known large black holes, the process is far beyond direct observation. The final evaporation of a black hole, if Hawking's semi-classical calculation is broadly right, lies in a future so distant that ordinary cosmic timescales become small. Stars will die. Galaxies will change. The cosmic microwave background will cool. Only then would large black holes begin to lose mass faster than they gain energy from their surroundings. This does not affect what happens to a spacecraft falling in today, but it affects the ultimate fate of information in the theory. The information paradox asks whether the details of what fell in are preserved in some subtle way. If they are, then the horizon is not the simple eraser it first appears to be. If they are not, then quantum mechanics must be modified. Most physicists expect information is not truly destroyed, but explaining how it is preserved without violating the smoothness of the horizon or the rules of causality remains a deep challenge. Recent theoretical progress has used ideas such as entanglement islands and holographic calculations to reproduce the page curve in certain models, suggesting that information can be recovered in principle from radiation after long times. But these are controlled theoretical settings, not direct observations of astrophysical black holes. The work is important because it shows possible consistency between gravity and quantum mechanics. It does not mean we can read a diary from Hawking radiation around Sagittarius A star. For the title's question, this distinction matters. What really happens beyond the event horizon is not answered by saying that anything is possible. It is answered by saying what our best theory predicts, where that theory is well supported, and where it likely breaks down. The horizon is well described. The crossing, for large black holes, may be locally uneventful. The interior leads inward. The singularity is a prediction and a warning sign. A black hole's surface area grows when matter falls in, at least classically. The area theorem, under ordinary assumptions, says the total horizon area does not decrease. In mergers, the final black hole's horizon area is larger than the sum in the appropriate sense. Gravitational waves carry energy away, but the horizon settles into a larger object. This behavior connects classical gravity with thermodynamic ideas, another reason horizons became central to physics. When two black holes merge, no material surface collides, but the spacetime outside rings. The ring down is like a struck bell only as an analogy. The frequencies depend on the final black hole's mass and spin. LIGO and Virgo measure these patterns as strain. Future detectors may test them with greater precision, looking for deviations that could hint at new physics near horizons. So far, the signals fit general relativity remarkably well. The absence of deviations is itself information. Many speculative alternatives to black holes predict echoes, surfaces, or modified ringdowns. The data can constrain those possibilities. It does not prove that every detail of the classical interior is correct, because the interior remains hidden. But it tells us that the exterior behaves very much like the black holes of general relativity in the regimes we can observe. The Event Horizon Telescope also tests the exterior. Its images depend on plasma physics, telescope coverage, calibration, and algorithms, so they are not simple snapshots of pure geometry. Still, the size of the ring in M87 is consistent with expectations for a black hole of its measured mass and distance. Polarized images add information about magnetic fields near the horizon. Future observations may sharpen the structure and track changes over time. A telescope array like the ET works because radio waves from the same distant source arrive at widely separated antennas. By comparing the signals with precise timing, astronomers reconstruct information equivalent to what a much larger telescope would collect. The process is called Very Long Baseline Interferometry. It turns Earth into a measuring device. It also leaves gaps in the data, which is why careful imaging tests and independent teams matter. The public image of M87 looked simple. Behind it were weather conditions at high mountain sites, petabytes of data recorded on hard drives, calibration pipelines, synthetic tests, and independent reconstructions. The darkness in the center was not accepted because it looked dramatic. It was accepted because the feature persisted through analysis and matched predictions. That is how a black hole becomes an object of evidence rather than an idea. Still, an image of a ring does not open the horizon. It gives us the silhouette of a region whose interior remains causally disconnected. Even perfect images of the shadow would not show what happens after crossing. They would show how light behaves just outside, and perhaps how plasma approaches the boundary. The last step remains theoretical, because no outgoing light carries interior news back to the telescope. The same is true for simulations. Supercomputers can model magnetized plasma in curved spacetime, producing synthetic images for comparison with ET data. These simulations are powerful because they connect theory with observation. But they are not reality by themselves. They require assumptions about particle heating, magnetic fields, electron distributions, and turbulence. A good simulation earns trust by reproducing measured features and by making predictions that observations can test. Black holes force astronomy to work at the edge of inference. The object is defined by a region that cannot communicate outward, so everything known observationally comes from the boundary's effects. The star that whips around Sagittarius A star does not enter the horizon. The radio ring around M87 comes from outside. The gravitational wave from a merger comes from the changing exterior geometry. The interior remains inferred from the equations that also explain those external facts. This is not unusual in physics. No one sees an electron's wave function directly. No one watches the core of the sun with ordinary light. No one touches the cosmic microwave background at the moment it was released. Science often builds reliable knowledge from indirect traces. Black holes are extreme because the traceable region ends at a mathematically precise boundary. That makes the inference both powerful and limited. The interior also raises a question about what it means for time to pass. For the falling object, proper time to the singularity is finite. For distant observers, the object's emitted light becomes increasingly delayed and redshifted. These are not two different universes. They are different slices through the same spacetime. Relativity allows them to coexist, though human intuition does not easily hold both at once. If a clock falls toward the horizon while sending pulses outward, A distant receiver gets the pulses at longer and longer intervals. The clock seems to slow. The light shifts toward radio wavelengths and then beyond practical detection. The clock is not seen crossing in the simple external coordinate description, but the clock itself, if not destroyed earlier, crosses in finite proper time. The event is real locally, even when it disappears observationally. This fading has consequences for how black holes grow in external descriptions. From far away, infalling matter appears to pile near the horizon, becoming dim and redshifted. In practical astrophysics, the black hole's mass increases, the external gravitational field changes, and the horizon grows. The coordinate puzzle does not prevent black holes from forming or merging. It tells us that descriptions of time near horizons require care. The horizon of a growing black hole is not a static painted sphere. In realistic collapse and accretion, horizons can form and change. There are event horizons, which depend on the entire future of spacetime, and apparent horizons, which can be identified more locally in simulations. This distinction matters to relativists. For a documentary explanation, the central point is that trapped regions form when gravity becomes strong enough that outward light can no longer escape. Because event horizons depend on the global future, they are not objects one could detect with a local handheld meter at the exact crossing. An infalling observer does not necessarily hear an alarm in the laws of physics at the boundary. The horizon's meaning is revealed by trying to send a signal to infinity and discovering that no future path succeeds. It is a boundary of possible communication, not a material surface. The lack of a surface distinguishes black holes from neutron stars. A neutron star has a surface, or at least a material outer layer. Matter falling onto it can strike, heat, and emit. A black hole has no such surface outside the horizon. Matter can radiate before crossing, but after crossing it does not hit a visible crust and send energy back. Observational tests have looked for signs of surfaces in compact objects. The absence of such signs supports the black hole interpretation. Neutron stars are already extreme, with masses greater than the Sun compressed into cities' worth of radius. Their gravity is strong, their magnetic fields can be immense, and their interiors contain matter at densities beyond atomic nuclei. Black holes begin where even that kind of support fails. They are not just heavier neutron stars, they are objects where the escape boundary closes and spacetime develops a horizon. The transition from neutron star to black hole can occur in a core collapse supernova or in the merger of neutron stars if the remnant is too massive. Sometimes a neutron star merger may briefly form a hypermassive neutron star before collapsing into a black hole. Gravitational waves, gamma-ray bursts, kilonova light, and neutrinos can all help study these events. The formation of the horizon itself remains hidden, but the surrounding signals reveal the conditions around it. The question of what crosses the horizon can include ordinary matter, radiation, magnetic fields, and information. Once energy crosses, it contributes to the black hole's mass and spin. From outside, the details become inaccessible except through their effect on those global properties. A black hole made from collapsed iron, hydrogen gas, or radiation can settle into the same external form if mass and spin match. That erasure of visible detail is both elegant and troubling. In classical relativity, nothing special has to happen to the infalling matter at the horizon. The matter does not know it has passed the point of no return if local conditions are gentle. But quantum theory complicates the story because horizons affect the definition of particles and vacuum states. Hawking's calculations showed that quantum fields near a horizon lead distant observers to see radiation. The vacuum itself is not a simple universal emptiness. The common picture of particle, pairs at the horizon, one falling in and one escaping, is a useful illustration, but not the full calculation. Hawking radiation comes from quantum field theory in curved spacetime and the relationship between modes near the horizon and modes at infinity. The simplified image can help intuition, but it should not be mistaken for tiny particles popping out of a surface like sparks from metal. The real mathematics, is subtler. For astrophysical black holes, Hawking radiation is overwhelmed by the environment. The cosmic microwave background is warmer. Accretion, even at low levels, adds more energy. A stellar mass black hole gains more from its surroundings than it loses. Only in an extremely cold, far future would evaporation dominate. This is why black holes are treated as effectively black in observational astronomy today, even though theoretically they have a temperature. The temperature of a black hole decreases as mass increases. A supermassive black hole is colder than a stellar mass one. A hypothetical tiny black hole would be much hotter and evaporate more quickly. But no confirmed primordial black holes have been observed. Searches for their effects continue in different forms, including microlensing, gamma-ray backgrounds, and gravitational signatures. The possibility remains speculative unless evidence appears. Primordial black holes, if they exist, would not form from stars. They would come from density fluctuations in the early universe. Their masses could span a wide range depending on the conditions. Some have been proposed as dark matter candidates, but observations strongly constrain many mass ranges. This shows again how black hole ideas connect to cosmology without turning every unknown into certainty. A possible population is not the same as a detected one. Most confirmed black holes are linked to stars and galaxies. Stellar mass black holes come from the deaths of massive stars and mergers. Supermassive black holes occupy galactic centers. Intermediate mass black holes, between these categories, are harder to confirm but increasingly important. They may form in dense star clusters or through mergers and could help explain how supermassive black holes grew. The evidence is developing, but the population is not yet mapped in the same way. Every class shares the horizon. A black hole's mass changes the scale, not the basic causal rule. The event horizon radius grows in proportion to mass for a non-rotating black hole. Double the mass, double the radius. But density inside the horizon, if averaged crudely over the volume, decreases for larger black holes. A supermassive black hole can have a low average density by that measure, even though the central curvature becomes extreme in the classical interior. This is another place where simple language can mislead. Calling a black hole infinitely dense points toward the singularity, but the horizon itself can enclose a huge volume. The density one calculates by dividing mass by the horizon volume is not the density of a material object. It is a rough comparison. A black hole is not a ball of matter with a surface. It is a region of space-time whose mass curves the geometry so strongly that escape is impossible. If you crossed the horizon of a supermassive black hole, the outside universe would not instantly vanish from view. Light that entered after you could still reach you. Depending on your motion, the sky could appear distorted, blue-shifted in some directions, red-shifted in others, compressed by aberration and gravitational lensing. But the ability to see something is not the ability to reach it. The outside could remain visible while no longer being part of your possible future. The closer you move toward the central region, the stronger the tidal effects become. Objects that were once stable are pulled into streams. Atomic and nuclear structures eventually cannot remain intact under the classical growth of curvature, though the exact final description requires physics beyond current confirmation. The falling object's history, chemistry, and structure are crushed out of any recognizable form long before the mathematical endpoint is reached. For a stellar mass black hole, this destruction may begin outside or near the horizon. For a supermassive black hole, it may happen well inside. That difference creates the strange possibility that crossing the horizon of a giant black hole could be less immediately violent than approaching a small one. The black hole with more mass can be gentler at the boundary because its curvature changes more gradually over larger distances. This does not make supermassive black holes safe. Their accretion environments can be deadly, and their interiors still end in finite proper time, according to classical theory. It only means that the horizon is not automatically the place where the body is torn apart. In black hole physics, danger depends on gradients, radiation, orbit, mass, and environment. The boundary itself is a causal threshold, not necessarily a mechanical blade. Consider a probe falling into a quiet, supermassive black hole while transmitting a signal. Engineers far away would see its data slow, redden, and fade. The probe's clock would appear increasingly delayed. Its final messages would become harder to separate from background noise. The probe, in its own frame, would continue inward after the last useful signal had already been sent. The moment the outside loses contact is not necessarily the moment the probe is destroyed. Inside, the probe could still record local measurements for a while, but those measurements would have no path back to the engineers. Its archive would become part of the hidden interior. This is the cleanest meaning of beyond the event horizon. Not that events stop happening. Not that physics becomes meaningless at once, but that the events are removed from the shared record of the outside universe. A black hole therefore divides reality in an operational way. Outside, there are observations, signals, comparisons, archives, and corrections. Inside, there may be a well-defined local sequence for the falling matter, but it cannot become part of the external scientific record by direct communication. The interior is not observable in the ordinary sense. It is reconstructed from theory and from the boundary behavior that theory predicts. The phrase "frozen at the horizon" is often used, but it should be handled with care. The falling object does not freeze in its own time. The image received far away fades toward invisibility. In practice, finite sensitivity, background radiation, and quantum effects mean no observer watches a crisp object hovering forever. What remains is a mathematical limit in one description and a physical disappearance from detectable signals. The horizon also affects causality for events inside. Suppose two observers cross at different times. Their ability to meet or exchange signals depends on their paths, the black hole's size, and the interior geometry. Inside does not mean all events are mutually connected in simple ways. Causal structure remains important. Relativity does not become chaos at the boundary. It becomes stricter, with fewer routes to choose from. For non-rotating black holes, the maximum proper time from horizon to singularity depends on mass. Around a stellar mass black hole, it can be tiny. Around a supermassive one, it can be much longer, perhaps hours for the largest cases. These are not travel times to another place. They are finite intervals before the classical endpoint. More mass gives more interior time, but it does not give an escape route. If the black hole is feeding, the infalling observer may encounter radiation from matter that crossed before or after them, blue-shifted by the geometry and motion. Real interiors may be affected by streams, fields, and perturbations. The clean textbook vacuum solution is a foundation, not a complete astrophysical environment. A star collapsing into a black hole accreting gas, and a black hole merging with another all have different surrounding conditions. The interior of a black hole formed by realistic collapse may contain infalling matter, radiation, and gravitational waves. It is not guaranteed to be the same as the eternal black hole drawn in ideal diagrams. Eternal solutions are useful because they reveal mathematical structure, but the universe builds black holes through processes in time. That difference matters especially when asking about the actual interior rather than the simplified geometry. The singularity theorems showed that under broad conditions, general relativity predicts incomplete paths in gravitational collapse. This was a profound result because it meant singularities were not just artifacts of perfect spherical symmetry. Collapse could generically lead to places where the classical theory ends. But the theorem does not tell us what quantum gravity replaces that ending with. It tells us where the old description cannot be the final one. A complete answer may require understanding spacetime at the Planck scale, where lengths and energies are so far beyond direct experiment that ordinary intuition fails. The Planck scale is not simply a tiny version of familiar space. It is where quantum uncertainty and geometry may become inseparable. Black holes are one of the few natural systems that force those issues into the same problem, which is why they remain central to theoretical physics. The cosmic censorship conjecture is another idea connected to interiors. Roughly, it suggests that singularities formed in realistic collapse are hidden behind horizons, preventing naked singularities from being visible to distant observers. This is not fully proven in all possible situations. But the observed universe has not presented a clear naked singularity. If horizons hide the breakdown of classical physics, they also protect the outside world from directly seeing that breakdown. In that sense, the event horizon is both a boundary and a veil. It hides the region where known equations reach their limit. It allows the outside black hole to remain simple and predictable, while the interior may be extreme and unresolved. Astronomers can measure mass and spin without knowing the final quantum state of the collapsing matter. The universe lets us study black holes from the outside while withholding the deepest part. For galaxies, the hidden part may not matter much on daily scales. What matters is the energy released before crossing. Accretion can heat gas, jets can inflate bubbles in galaxy clusters, quasar winds can move material across thousands of light years. These effects come from outside the horizon, where matter still interacts with the universe. The interior can remain inaccessible, while the black hole's environment becomes one of the most influential engines in astrophysics. In galaxy clusters, supermassive black holes can help prevent hot gas from cooling too quickly. X-ray telescopes see cavities and bubbles in the intracluster medium, inflated by jets from central galaxies. Without such feedback, some clusters might form stars at rates much higher than observed. The central black hole, through energy released by accretion, becomes part of a larger thermal balance. The horizon is tiny compared with the cluster, but the consequences of matter approaching it are enormous. This scale difference is one of the strange features of black holes. The horizon of a supermassive black hole may be smaller than the solar system, while the jet it helps power can extend far beyond the visible galaxy. The causal boundary itself is compact. The influence of accretion spreads through plasma, radiation, shocks, and magnetic fields. The black hole interior is hidden, but the surrounding universe records the approach. The early universe may have used black holes as engines before galaxies were fully mature. Quasars at high redshift show that some supermassive black holes grew rapidly. The light from those quasars is stretched by cosmic expansion before reaching our telescopes. Infrared instruments can study them because their ultraviolet light has been redshifted into longer wavelengths. Each distant quasar is both a black hole system and a timestamp from cosmic history. To grow so large so early, a black hole needs seeds and fuel. Dense gas, mergers, and favorable conditions may help. But radiation from accretion can push gas away, limiting growth. The problem is a balance between feeding and feedback. Observers search for faint active nuclei, early galaxies, and signatures of massive seeds. Simulators test whether gas can collapse directly or whether star remnants can merge fast enough. The answer is still being refined. These early black holes also remind us that horizons formed long before any mind could ask about them. While the first generations of stars were changing the chemistry of the universe, compact objects were already bending light and trapping futures. Their interiors were hidden then as now. The difference is that today a small planet around an ordinary star has instruments sensitive enough to detect their distant consequences. A black hole in a star cluster may grow through collisions and mergers. Dense clusters can bring massive stars and remnants close together. If intermediate mass black holes exist in significant numbers, they could serve as stepping stones between stellar remnants and supermassive galactic centers. Evidence for them includes unusual X-ray sources, stellar motions in clusters, and gravitational wave events with heavier masses. But each candidate must be handled carefully because other explanations can imitate some signals. The universe does not label its objects. A bright X-ray source might be a stellar mass black hole accreting above expectations, an intermediate mass black hole, a neutron star, or a beamed source depending on details. Astronomers have to combine luminosity, spectra, timing, environment, and dynamics. Black holes often announce themselves through ambiguity first. Only repeated measurements narrow the possibilities. The same caution applies to claims about what lies beyond the horizon. Popular culture often fills the unobservable with tunnels, other universes, or shortcuts. Physics allows mathematical discussions of wormholes and extended spacetimes, but known astrophysical black holes do not provide evidence for usable passages. The event horizon we observe indirectly behaves as a one-way boundary. The interior predicted by classical collapse is not a transit system. A wormhole, if it existed in a traversable form, would require conditions not known to occur in ordinary black hole formation. It would have to remain open against collapse, likely requiring exotic negative energy densities or other physics not demonstrated at macroscopic scales. The black holes formed by stars and mergers are not expected to be traversable wormholes. The resemblance in diagrams is not evidence of actual passage. The reason this matters is that black holes are already strange without exaggeration. A boundary in spacetime that one can cross without noticing locally, after which every future path leads inward, is enough. A star torn into plasma by tidal gravity is enough. A pair of black holes radiating several solar masses of energy as gravitational waves is enough. The measured universe does not need embellishment to become difficult. The scientific mystery is quieter and more demanding. How does spacetime encode information? What replaces the singularity? Does the horizon remain smooth for every infalling observer, or do quantum effects alter it in unexpected ways? How do magnetic fields launch jets from near-rotating horizons? How did the earliest supermassive black holes grow? These questions are not empty wonder. They are tied to equations, instruments, and data. A control room receiving a gravitational wave alert does not see a black hole. It sees a candidate event, a waveform, a sky localization, a set of probabilities, and a need for follow-up. Telescopes may search the region if a neutron star could be involved. For binary black holes, no light is usually expected. The event is carried by spacetime itself. The black holes merge invisibly, except for the distortion that passes through Earth. When detectors improve, more events appear. The catalog grows. Statistical patterns emerge. Mass distributions, spin orientations, merger rates, and possible formation channels become testable. Some black holes may form from isolated binary stars. Others may pair up dynamically in clusters. Some may belong to generations of mergers. The event horizon is the same kind of boundary, but the life history of each black hole may differ. The merger of two black holes also creates a final horizon that settles. During the most violent phase, spacetime is highly dynamic. Afterward, the remnant becomes a Kerr black hole if general relativity holds. The ringdown carries information about that settling. Future detectors with greater sensitivity may measure multiple ringdown modes, allowing stronger tests of whether the remnant is truly described by mass and spin alone. Space-based detectors planned for lower-frequency gravitational waves could observe supermassive black hole mergers, compact objects spiraling into massive black holes, and possibly signals from the early universe. Such observations would probe black hole environments and strong gravity in new regimes. They still would not see inside the horizon, but they would map the exterior with extraordinary precision, tightening the boundary between known and unknown. At the same time, electromagnetic telescopes are improving. Infrared observatories examine dusty galactic centers and high redshift quasars. X-ray telescopes study hot inner disks and flares. Radio arrays trace jets and horizon-scale emission. Optical surveys catch tidal disruptions. Each wavelength reveals a different part of the black hole environment. No single instrument tells the whole story. The object is assembled from many kinds of light, and sometimes from no light at all. The black hole itself remains dark, because light from inside cannot escape. But the region outside can be among the brightest in the universe. This contrast is central. The darkness is not mystical. It is a causal result. The brightness is not the whole shining. It is matter, still outside, surrendering gravitational energy. A quasar is a beacon built around a boundary that emits no classical light of its own. If a camera could hover safely near a black hole, the view would be dominated by gravitational lensing. Background stars would be warped into arcs and rings. The accretion disk could appear above and below the hole because light from the far side bends around. The dark region would be larger than the horizon due to photon capture and lensing. Human eyes evolved for gentle gravity, not for a sky where light can orbit. Photons can have unstable circular paths near a black hole. A small disturbance sends them either outward or inward. This photon region contributes to the appearance of the shadow. It is not a place where light rests calmly. It is a knife-edge set of trajectories in curved spacetime. The 8 ring is related to this structure and to the emission from plasma near the black hole, which is why interpreting the image requires both gravity and astrophysics. A black hole does not have to be surrounded by a beautiful ring. If little matter is present, it may be dark. If the accretion flow is tilted, turbulent, or variable, the image changes. If the black hole is part of a binary, the environment can be distorted. The public image is one case, not a universal portrait. What remains universal is the horizon defined by escape and the exterior geometry controlled by mass and spin. Inside the horizon, light emitted outward can still move outward locally for a time in some coordinate sense, but it cannot increase its radius enough to escape. This is one of the hardest points to express, because everyday language treats direction as obvious. In curved spacetime, future directed paths are constrained by geometry. Outward can become a direction that no future light path successfully completes. The cone has tipped too far. The falling observer may try to accelerate. Acceleration changes the world line, but not the causal structure. Inside the horizon, all future directed time-like world lines end at smaller radius in the simple black hole. This is why even a rocket moving at enormous speed cannot escape once crossing has happened. The speed needed is not merely greater than light. The concept of outward escape has ceased to exist in the future geometry. A distant observer never receives a signal saying, "I have crossed the horizon." The last signals arrive increasingly delayed and redshifted. This is why the horizon is not confirmed by direct crossing reports. Instead, evidence accumulates from compactness, accretion behavior, lack of surfaces, gravitational waves, and horizon-scale imaging. The conclusion is not based on a single dramatic observation. It is a convergence of many measurements. The phrase "beyond the event horizon" therefore points to a region that is physically real in the theory, but observationally sealed. If matter crosses, its mass energy remains part of the black hole's external gravitational field. The detailed arrangement becomes hidden. The outside can respond to the total mass and spin, but not to a message describing the interior state. The black hole becomes simpler from the outside than the matter that made it. This simplification has an astronomical consequence. Black holes are among the cleanest macroscopic objects in the universe, according to general relativity. A planet has mountains, atmosphere, magnetic field, oceans, chemistry, weather, and history. A settled black hole has mass and spin for most practical purposes. The object created by collapse loses the visible complexity of its origin. That is why the information paradox feels so sharp. Simplicity may be hiding a vast accounting problem. Some theories suggest the information is stored in subtle correlations on or near the horizon. Others suggest the interior and radiation are connected through entanglement in ways that change the naive picture. Holographic dualities show that in certain universes with different boundary conditions, gravitational physics can be equivalent to a quantum theory without gravity. These are not casual speculations. They are technical results, but translating them into our universe remains difficult. For a viewer of the sky, the practical black hole is still the one measured by telescopes. Sagittarius A star flares. M87 launches a jet. X-ray binaries change state. Gravitational wave detectors add mergers to catalogs. These observations do not solve the singularity, but they anchor the question. Any theory of the interior must agree with the exterior world that instruments already see. The final interior may be resolved by quantum gravity in a way no current image can show. It may avoid infinite curvature. It may encode information through degrees of freedom we do not yet understand. It may change the meaning of space-time itself. But until such ideas make testable predictions, the honest voiceover must hold them at the edge, not place them in the center as fact. Science has a habit of making the unknown more precise. Once, black holes were mostly an implication of equations. Now they are objects with catalogs, masses, spins, images, and waveforms. The unknown did not vanish. It moved inward. The exterior became measurable. The horizon became observationally supported. The singularity and information problem remained, sharper than before, because the objects themselves became harder to doubt. This movement inward is part of the history of astronomy. Mars changed from a wandering red light to a planet with craters, volcanoes, dust storms, and rovers. Stars changed from points to plasma spheres with spectra and life cycles. Galaxies changed from nebulae to island systems, and then to nodes in the cosmic web. Black holes have followed the same path, except the final boundary is not distance or resolution. It is causality. No larger telescope can see through an event horizon in the ordinary way. Better instruments can see closer to it, measure the ring more sharply, track plasma, test gravity, and constrain alternatives. They can observe matter before it crosses and gravitational waves as horizons merge. But the interior will not be revealed by simply collecting more light. It requires theory tested by what remains outside. This is why black holes connect observation and mathematics so tightly. A telescope image without relativity would be difficult to interpret. An equation without observation could drift away from nature. Together, they create a disciplined picture. The ring around M87, the orbits near Sagittarius A star, and the LIGO chirps are not isolated wonders. They are different ways the same gravitational theory meets the universe. Still, every observation has limits. The ET resolution is finite. Accretion models have uncertainties. Stellar orbits depend on precise astrometry and assumptions about extended mass. Gravitational wave parameter estimates come with probability distributions. Serious black hole science lives inside those error bars. The mystery is not created by ignoring uncertainty. It is made stronger by measuring uncertainty honestly. The event horizon itself is not a place where an astronaut could hover without effort. To remain fixed just above it would require enormous acceleration, increasing without limit as the horizon is approached in the ideal non-rotating case. Freefall is different. A freely falling object crosses without needing to resist gravity. Hovering near the boundary is what becomes impossible for ordinary rockets, not crossing. This distinction matters because many imagined journeys confuse hovering with falling. A station held just above a black hole would experience intense acceleration and likely a hostile radiation environment if gas were present. A falling probe feels weightless locally, though tidal forces grow. The horizon is easiest to cross by not trying to stay outside. It is hardest to escape once crossed, because there is no remaining escape. The black hole's mass sets the horizon scale, but the environment sets much of the danger outside. A quiet, isolated supermassive black hole might let a small object cross without immediate tidal destruction. An active stellar mass black hole in a binary might tear and irradiate matter before it nears the boundary. There is no single image that captures every case. Real black holes occupy different neighborhoods. A black hole in an X-ray binary is surrounded by the life of another star. Gas pulled from the companion carries angular momentum, forms a disk, heats, and sometimes erupts. A black hole in a galactic nucleus may be surrounded by stars, dust, and molecular clouds. A merging black hole pair may have almost no gas nearby. The horizon's definition is universal. The approach to it is local history. The phrase "what really happens" should therefore be answered in layers. Outside, matter can orbit, heat, radiate, and sometimes escape as part of a jet or wind. At the horizon, escape paths close. Just inside, local physics may continue normally for a brief time if tidal forces are mild. Deeper inside, all paths lead toward extreme curvature. At the final classical endpoint, our current theory reaches a limit, and quantum gravity is required. This layered answer is less dramatic than saying the horizon destroys everything instantly, but it is more accurate. It also makes the object stranger. A boundary that can be locally uneventful and globally absolute is not part of everyday experience. A place where the future points inward is more difficult to imagine than a violent surface. The true strangeness is geometric. Geometry sounds calm, but in relativity, geometry decides fate. It tells light where it can go. It tells clocks how they compare. It tells matter how to fall when no force pushes it. Near a black hole, geometry is not a passive stage. It is the central actor. The event horizon is a statement about the shape of all possible futures from a region of spacetime. A black hole also affects the meaning of distance. The radial coordinate used by distant observers does not behave like ordinary ruler distance near the horizon. Different coordinate systems can describe the same physics without singular behavior at the horizon. Some coordinates make the crossing look pathological, others pass smoothly through. The real singularity in the simple solution is not at the horizon, it is deeper inside, where curvature diverges. This is why physicists distinguish coordinate singularities from physical singularities. The horizon can appear problematic in one mathematical description, but that problem can be removed by choosing better coordinates. The central singularity cannot be removed in the same way within classical general relativity. Curvature itself becomes unbounded. The difference is crucial. The horizon is not a place where equations necessarily fail. The singularity is. For a large black hole, an astronaut crossing the horizon might not be able to identify the exact moment locally. For a small black hole, tidal forces could make the question irrelevant because destruction may occur before crossing. Both statements are compatible. The event horizon's local experience depends on curvature scale. The causal meaning does not. Crossing always means no return. Imagine the last usable telemetry from a probe falling toward a black hole. The signal arrives faint and stretched. Engineers compare timestamps, frequencies, and expected gravitational redshift. The final packet is not a dramatic goodbye. It is data fading into noise. After that, the probe's onboard clock may continue, but the mission has ended for the outside universe. Its later measurements exist only along a path that cannot reconnect. In a sense, black holes turn the scientific method back on itself. Science depends on observation, communication, and repeatable comparison. The event horizon is where communication fails by law, not by inconvenience. The universe places a limit on what can be shared. The response is not to abandon science, but to study the limit itself through everything it affects outside. Black holes are also laboratories for extreme energy conversion. Accretion can convert a larger fraction of rest mass into radiation than nuclear fusion in ordinary stars. This is why quasars can be visible across cosmological distances. The energy is released before matter crosses the horizon, as gas loses gravitational potential energy and angular momentum. The black hole does not need a surface to power brightness. The curved spacetime around it is enough. The efficiency depends on spin. Around a rapidly rotating black hole, the innermost stable orbit can lie closer to the horizon for matter orbiting in the same direction as the spin. This allows more energy to be released before plunge. Measuring this efficiency is difficult, but it connects observations of disks to the geometry of spacetime. Again, the outside tells us about the boundary without revealing the interior. Magnetic fields complicate the simple disk picture. In hot plasma, charged particles spiral along field lines, turbulence develops, and magnetic stresses move angular momentum. The magnetorotational instability is one mechanism that helps accretion disks function. Without a way to transport angular momentum outward, gas would keep orbiting rather than falling inward. The black hole is fed not by simple attraction alone, but by a disk's ability to rearrange motion. Jets show how not all matter near a black hole falls in. Some plasma is redirected outward at high speed. The jet may carry energy extracted from rotation and accretion. It can remain narrow over enormous distances, implying magnetic collimation and interaction with surrounding gas. In images of radio galaxies, the black hole's neighborhood is connected to lobes and hotspots far beyond the stars of the host galaxy. These jets can be seen long after the particles left the central region. Electrons radiate synchrotron emission as they move through magnetic fields. X-rays can mark shocked gas. Radio lobes can store energy for millions of years. The event horizon remains invisible, but the galaxy around it becomes a record of past feeding. A black hole's history is written in bubbles, filaments, and disturbed gas. The Milky Way has its own record. Structures above and below the galactic center suggest past energetic activity, though not necessarily from a quasar-level event. Sagittarius A star is quiet now, but galactic centers change. A cloud or star passing too close can trigger flares. On cosmic timescales, quiet and active are phases, not identities. The horizon waits through both. When we ask what happens beyond the event horizon, we should also ask what happens just before it. Most observable drama belongs to the outside. The disk glows before crossing. The star is torn before disappearing. The gravitational wave peaks as horizons merge. The telescope records photons that escaped, not photons that failed. Astronomy lives in the last light, last orbit, last wave, and last signal from the reachable side. The reachable side is not small. Around black holes, there are coronae of hot electrons, disks with changing states, broad iron emission lines shaped by relativity, masers tracing gas in galactic nuclei, and stars making close approaches. Each provides a different measurement. The event horizon is the final boundary, but the region outside can be rich enough to occupy generations of observers. Some of the strongest black hole evidence comes from stars around Sagittarius A star. The star S2, also known as S02, follows a highly elliptical orbit and passed close to the central mass. Its motion allowed tests of relativistic effects, including gravitational redshift. The orbit is not a sketch. It is a measured path built from years of infrared observations. Dust hides the galactic center in visible light, but infrared light can get through. Those stellar orbits are a reminder that black holes are not only destructive. Around the Milky Way's center, stars continue moving. Gas clouds orbit. The black hole is massive, but the galaxy is not being consumed wholesale. Gravity organizes motion. Only objects with paths that take them too close, or gas that loses enough angular momentum, approach the horizon. Most of the galactic center remains outside, dynamic and observable. Near a supermassive black hole, stars can survive close passages if they remain outside the tidal disruption radius. For some combinations of black hole mass and star type, the tidal disruption radius lies outside the horizon. For very massive black holes, a sun-like star could cross the horizon before being torn apart. At least in simple estimates, this means the same kind of star can have different fates depending on black hole mass. The tidal disruption radius depends on the star's density and the black hole's mass. A white dwarf, being dense, can approach closer before disruption. A giant star can be torn farther out. These details make tidal flares diverse. Observers use light curves, spectra, and host galaxies to infer what happened. Again, the event horizon itself remains unseen, but the material response outside becomes evidence. White dwarfs, neutron stars, and black holes form a sequence of compact remnants, but only black holes have horizons. A white dwarf is supported by electron degeneracy pressure, a neutron star by neutron degeneracy pressure and nuclear interactions. A black hole forms when no known pressure can support the mass against collapse. The event horizon is the sign that gravity has crossed from extreme object to trapped region. The gravitational radius of a black hole scales with mass, but the timescales around it also scale. Matter orbiting near Sagittarius A star changes on minutes. Matter near M87's black hole changes over days or longer because the black hole is much larger. This affected ET imaging. Sagittarius A star is close but variable, like trying to photograph a moving subject during a long exposure. M87 is farther but steadier on observing timescales. The 8 image of Sagittarius A star required handling rapid variability. The final image represents an average structure, not a single ordinary snapshot. It still showed a ring-like feature consistent with a black hole shadow. The difficulty itself teaches something. Horizon-scale environments are not fixed sculptures. They are turbulent systems where plasma moves, brightens, and fades while gravity sets the stage. Future arrays may add telescopes, improve coverage, and observe at higher frequencies. Space-based baselines could one day sharpen the view. Movies of black hole plasma may become possible. Such observations would test accretion physics and strong gravity. They would not make the horizon transparent, but they would show the reachable region changing in real time. The boundary would remain dark in a more detailed frame. When matter finally crosses, its observable electromagnetic story ends. But the black hole's mass grows by the energy that entered. If the matter carried angular momentum aligned or misaligned with the spin, it can change the spin. If enough matter falls in over time, the horizon expands. From outside, the black hole incorporates what it cannot reveal. The details become hidden, while the totals remain gravitationally present. In classical physics, the event horizon prevents any violation of causality from escaping the singularity. In quantum physics, the horizon raises the question of how degrees of freedom are counted. These two views do not yet fit together completely. Black holes are where both are necessary. Too much gravity for quantum field theory to ignore curvature. Too much quantum structure for general relativity to be final. The lack of a complete theory does not mean nothing is known. This is a common mistake. We know how black holes affect orbits. We know how merging black holes radiate gravitational waves. We know how accretion can produce high-energy emission. We know the event horizon's role in general relativity. The unknown is specific, the full quantum description of the interior, the singularity, and information across the lifetime of evaporation. The difference between mystery and ignorance matters. A mystery in science is not a blank space to be filled with anything. It is a structured problem surrounded by evidence. Black holes are structured in exactly this way. The more we measure them, the more precise the remaining questions become. The horizon is no longer merely imagined. It is a working part of models that match real data. For a falling object, the most profound change after crossing is not necessarily sensory, it is causal. The set of possible futures loses every path back out. A person could still look at an instrument, feel weightless briefly, and watch local physics continue. But all choices now unfold inside the black hole. The outside universe has become part of the past light entering the interior, not a destination. The event horizon also separates histories. From the outside, the object becomes part of the black hole's mass and spin. From its own path, it continues toward the interior. In quantum terms, how these descriptions fit together becomes part of the information problem. In classical terms, there is no contradiction. The outside cannot see the crossing completed, and the infaller crosses in finite time. This duality of descriptions is not unique to black holes, but horizons make it unavoidable. Relativity often asks us to accept that different observers slice spacetime differently. Black holes push that lesson to its edge. The horizon is where no shared future signal can reconcile the accounts. The mathematics keeps them consistent, while intuition strains to follow. A useful restraint is to avoid imagining the black hole interior as a room. It is not a chamber behind a door. The horizon is not an entrance to a cave. Space and time inside are arranged differently from the familiar exterior. There may be volume in mathematical slicings, and there may be local experiences for infalling matter, but the region is not a place one can occupy permanently or map from outside. Some calculations show that black hole interiors can have surprising volumes depending on how spacetime is sliced, even while the horizon area is finite. This is mathematically interesting and connected to questions about entropy and complexity, but it should not be confused with a safe internal landscape. Volume in a relativistic spacetime is slice-dependent. The unavoidable future toward extreme curvature remains in the classical picture. If two observers cross the horizon of a large black hole at different times, the earlier one may or may not be able to receive signals from the later one, depending on trajectories. The causal structure inside is not trivial. The singularity, in the non-rotating case, cuts off future paths. The interior is a dynamic region of endings, not a static container. The event horizon is only the outer boundary of that causal structure. The best visual metaphors are often imperfect. A waterfall analogy can help. Upstream, a fish can swim against the current. At the point where the water flows faster than the fish can swim, escape upstream becomes impossible. Downstream, the fish can still move locally, but the river carries every path over the falls. The black hole version uses space-time and light rather than water and fish, but the causal lesson is similar. Even that analogy fails if pushed too far. Light does not swim through space as a fish through water, and space-time is not a substance flowing in an ordinary river. But analogies are stepping stones. They help the mind approach the equations, then must be left behind. Near a black hole, the equations have the final authority because ordinary experience has no matching case. A black hole's horizon area is proportional to the square of its mass for a simple non-rotating case. When mass increases, the radius increases, and the area grows faster. The entropy associated with that area is enormous. A black hole can have more entropy than ordinary matter filling the same region. This is one reason black holes dominate discussions of the universe's long-term thermodynamic future. Over immense time, as stars fade and galaxies exhaust gas, black holes may become the last major reservoirs of mass energy in bound structures. They can merge, drift, and eventually evaporate if Hawking radiation remains the correct description. The future of black holes stretches far beyond the lifetimes of stars. The event horizon is not only a present boundary, it may be a long-lived feature of the universe's far future. But for the universe we observe now, black holes are active participants in cosmic structure. They form from stars, grow in galaxies, merge across spacetime, and light up when fed. They are not rare mathematical curiosities. Stellar mass black holes likely number in the millions or more within a galaxy like the Milky Way. Most are quiet and difficult to find, because darkness is their normal state. Quiet black holes may drift unseen through the galaxy. If one passes near a star from our point of view, gravitational lensing can reveal it. If it has a companion, accretion can reveal it. If it merges, gravitational waves can reveal it. Otherwise, it may leave little trace. The galaxy could contain many horizons without many lights. The visible black holes are the ones nature has arranged into detectable situations. This makes the event horizon both common and hidden. It may exist around countless stellar remnants, yet each one is small and dark, unless circumstance provides a signal. The most famous images show supermassive black holes because their horizons are large enough in angular size or their environments are bright. The ordinary population is mostly inferred statistically through stellar evolution and detected systems. The black hole's lack of surface also affects how it accretes. Matter approaching a neutron star can release energy at the surface. Matter approaching a black hole can advect energy through the horizon, disappearing from the observable flow. This difference helps explain why some black hole systems are dimmer than comparable neutron star systems in certain states. The missing surface is not directly seen, but its absence changes the light. In low luminosity accretion flows, gas may be hot and inefficient at radiating. Much of the energy can be carried inward. For a black hole, that energy can cross the horizon. For an object with a surface, it should eventually be emitted when the gas lands. Comparing systems helps test whether a horizon is present. These arguments are model-dependent, but they add to the broader evidence. The horizon is a prediction that survives attempts to replace it. Alternative compact objects have been proposed, from boson stars to gravastars and other exotic possibilities. Some might mimic black holes under certain conditions. Observations of ringdowns, shadows, accretion, and surface emission constrain them. The door is not closed by assumption. It narrows as data improve. So far, ordinary black holes remain the simplest explanation for many systems. Simplicity in physics does not mean blandness. A black hole described by mass and spin can still create some of the richest phenomena in the universe through its environment. The complexity moves outside: disks, jets, stars, turbulence, magnetic fields, radiation, and galaxy-scale feedback. The interior remains hidden. The exterior becomes a laboratory where the hidden object's presence is impossible to ignore. The title asks about beyond, but a careful answer keeps returning to the edge because that is where knowledge is anchored. Beyond the horizon, no direct signal. At the horizon, causal closure. Outside the horizon, evidence. This three-part structure is the honest map. It does not satisfy every imaginative question, but it separates what is measured, what is predicted, and what remains unresolved. A probe falling through the horizon of M87's black hole, if somehow protected from the environment, would have a very different scale around it than a probe falling into a 10 solar mass black hole. The horizon would be immense. Tidal forces at crossing could be small. The central future would still await. The scale changes the experience, but not the one-way nature of the boundary. A photon emitted from just outside the horizon can escape only if aimed within a narrowing set of directions. The closer to the horizon, the more difficult escape becomes. At the horizon, the outward escape direction closes. Just inside, none remain. This continuous narrowing helps replace the idea of a sudden wall with the idea of a causal transition. The boundary is exact, but the conditions around it change smoothly in the local geometry. From the outside, the event horizon also has a temperature and entropy in the thermodynamic description. This is not a surface of hot material, it is a property of the horizon in quantum field theory and gravitational thermodynamics. The idea that geometry can have thermodynamic behavior is one of the deepest lessons black holes taught physics. It suggests that space-time may have microscopic degrees of freedom, though we do not yet see them directly. The laws of black hole mechanics were discovered as analogies to thermodynamics before Hawking radiation made the analogy literal. Surface gravity resembled temperature. Horizon area resembled entropy. Energy, spin, and charge followed relations like thermodynamic laws. Then, quantum theory gave black holes a temperature. What began as formal resemblance became a clue that gravity and thermodynamics are connected at a fundamental level. This connection reaches beyond black holes. Some physicists suspect that space-time itself may be emergent from quantum entanglement or statistical structure. Black holes provide the sharpest examples because their entropy is so large and their horizons so precise. Whether this suspicion becomes a complete theory remains unknown. But the event horizon has already changed how physicists think about reality, not only about collapsed stars. In ordinary astronomy, a boundary is usually a surface or edge of material. A planet has a surface or atmosphere. A star has a photosphere, not a solid edge, but a layer where light escapes. A nebula fades into surrounding gas. A black hole horizon is different. It is not made of matter. It is an edge in causal possibility. That makes it unlike almost every familiar boundary in the sky. If an object crosses a planet's horizon, in the ordinary visual sense, it can reappear. If a spacecraft passes behind the moon, radio contact can return when geometry changes. If a probe descends behind Jupiter, a relay might recover signals if positioned correctly. A black hole event horizon has no such workaround. The loss of contact is not line-of-sight blockage. It is the closing of all future outward causal paths. That is why the horizon's name is apt, but imperfect. On Earth, the horizon is where sight ends, because the planet curves away, but you can travel beyond it and return. Around a black hole, the event horizon is where return itself ends. It is a horizon not for vision alone, but for events that can ever affect distant observers. The name is gentle for something absolute. The interior also changes how we think about ownership of events. An explosion inside the horizon, if such a thing occurs in local terms, cannot brighten the outside sky. A message written inside cannot be mailed out. A measurement recorded inside cannot join a public archive. The outside universe only knows the black hole's global properties. The rich local story becomes causally private. Physics usually dislikes private stories because science is built on shared evidence, yet relativity allows regions that cannot communicate. Cosmological horizons also limit what we can observe in the expanding universe. Black hole horizons are more local and more severe. They show that the universe is not obligated to make every event part of every observer's possible record. The cosmic horizon hides distant galaxies whose light will never reach us because of expansion. A black hole horizon hides events because gravity has closed escape paths. These are different horizons, but both teach limits. Astronomy is not the study of everything that exists. It is the study of what can leave traces available to us, plus the disciplined theory of what those traces imply. In black hole science, traces are often extreme. A star moving at thousands of kilometers per second near the galactic center. A disk line broadened by relativistic motion and gravity. A gravitational wave chirp crossing Earth after traveling for hundreds of millions or billions of years. A radio ring measured in micro-arcseconds. Each trace points toward a horizon without crossing it. The event horizon is also a practical limit for any future exploration. No advanced spacecraft, under known physics, can return after crossing. This is not an engineering challenge waiting for better engines. It follows from the role of light speed and space-time geometry in relativity. Engines can change paths within the future light cone. They cannot move an object outside the light cone or create a new external future from inside. This makes black holes useful for testing the difference between hard and impossible. It is hard to image a black hole shadow, but possible with enough telescopes and analysis. It is hard to detect gravitational waves, but possible with interferometers. It is impossible, under known physics, to send a signal from inside the horizon to outside. The first two yielded to technology. The third is part of the theory's causal structure. Could future physics change that? A complete quantum gravity theory may revise our understanding of horizons in subtle ways, especially over evaporation timescales. But any revision must explain why classical horizons work so well for astrophysical observations. It cannot simply allow ordinary escape without consequences, because we would expect evidence of surfaces, echoes, or violations already constrained by data. New physics has to be careful physics. The discipline of black hole research comes from this balance. Remain open to deeper theory, but respect existing measurements. Allow the singularity to signal incompleteness, but do not pretend the horizon is untested. Explore quantum information, but do not turn speculation into a travel brochure. The most accurate black hole is stranger than fantasy because its strangeness is constrained. In the final seconds before a small black hole destroys an infalling object, tidal forces would dominate every material process. Molecular bonds, atomic structures, and eventually nuclear matter would be subjected to gradients beyond ordinary survival. In a large black hole, the same fate might be delayed, not avoided. The deeper interior is where the geometry becomes lethal. The horizon is the commitment to that future. For matter, the crossing is not a magical erasure. Energy and momentum remain part of the space-time. The black hole responds by changing mass and spin. In a full quantum description, something must account for information. The fact that our current theories struggle with that accounting does not make the matter vanish from physics. It makes black holes one of the places where physics is unfinished. The singularity, if left in the classical picture, is not a destination one survives to examine. It is the end of time-like paths. The word center suggests a location in space, but inside the horizon the singularity is better understood as an unavoidable future boundary in the simple case. This is another reason ordinary mental pictures fail. The center is not merely down. It is later. A falling observer cannot choose to orbit inside a non-rotating horizon the way a satellite orbits Earth. Stable circular orbits end it outside. Even light cannot maintain a stable escape-capable orbit. The geometry has passed the point where familiar orbital mechanics applies. The object is not moving through a normal region with a strong central pull. It is inside a trapped region where futures converge. In a rotating black hole, there are more complicated possibilities in the ideal solution, but instability and realism matter. Physicists study mass inflation near inner horizons, perturbations, and the effects of fields. These are not decorative details. They may determine what the interior of a real spinning black hole is like. The simple question has a complicated answer because real black holes rotate and real universes disturb them. This is why a script about black holes should not promise final certainty beyond the horizon. It can say what general relativity predicts. It can say what observations support outside. It can say where quantum gravity is needed. It can explain why crossing is one way. The remaining unknown is not a failure of imagination. It is the frontier where theory has not yet met decisive evidence. The horizon's one-way nature also gives black holes a role in thought experiments. Physicists lower boxes of radiation toward horizons, ask how entropy changes, consider what an outside observer can know, and test the limits of thermodynamics. These thought experiments are not games. They sharpen definitions. Black holes expose hidden assumptions in our ideas about heat, information, time, and measurement. The generalized second law says that ordinary entropy outside plus black hole entropy should not decrease. If matter with entropy falls in, the black hole area increases enough to compensate. This idea protects thermodynamics in a universe with horizons. It also suggests that the horizon area represents something physically countable. The exact microscopic accounting remains one of the deep goals. Holography grew partly from this. If the entropy of a black hole scales with area, Perhaps the information content of a region of space can be represented on a boundary. In certain theoretical frameworks, this becomes precise. In our universe, the lesson is still being interpreted. But the event horizon was the clue. A surface that is not material taught physics to count information differently. This is a long way from the first simple idea of a dark star. In the 18th century, Jean Michel imagined objects whose gravity could keep light from escaping in a Newtonian sense. Later, general relativity changed the meaning completely. The modern black hole is not merely a star with high escape velocity. It is a space-time geometry with a horizon, predicted by Einstein's theory even though Einstein himself was cautious about such objects. The term black hole became common only in the 20th century. Before that, the solutions and collapsed objects had other names. The concept matured as relativity, stellar evolution, nuclear physics, and observation came together. A black hole needed not only equations, but a way for nature to make one. Massive stars, compact remnants, and galactic nuclei provided that path. Instruments provided the evidence. Now, black holes are part of standard astrophysics. Students calculate Schwarzschild radii. Observatories schedule campaigns on accreting systems. Gravitational wave alerts report mergers. Space telescopes monitor flares. The extraordinary has become a working category. Yet the interior remains extraordinary in the older sense, still beyond direct reach, and still capable of unsettling the foundations of theory. The public often meets black holes through danger. A planet being swallowed, a star destroyed, a final plunge. Those events are real possibilities in the right conditions, but they are not the whole object. A black hole can also be quiet for millions of years. It can sit in a binary, alter a companion, wait in a galactic center, or drift unseen. Its most defining property is not violence, it is the horizon. A quiet black hole is perhaps more conceptually pure. Remove the disk, the jet, the flare, the companion. Leave only mass, spin, and the causal boundary. Nothing glows. Stars behind it distort slightly if the alignment is right. A passing object crosses and never returns. The simplicity becomes stark. The universe has made a region that keeps its future to itself. But the universe rarely gives us pure cases. We find black holes through messiness, gas, companions, mergers, crowded centers, bright disks, and chance alignments. The clean theoretical object is studied through dirty astrophysical evidence. This is not a flaw. It is how nature works. The horizon may be simple, but the route to knowing it is full of dust, plasma, noise, and patient correction. Data archives hold many black hole stories. A decades-long sequence of infrared images at the galactic center. X-ray light curves from binaries. Radio maps of jets. Gravitational wave strain data. Spectra from active nuclei. Each file is a narrow contact with an object that itself withholds direct contact. The archive becomes a map of the accessible edge. A scientist comparing two images of a tidal flare is not watching matter inside the horizon. They are watching the last external reorganization of a star. A researcher fitting a waveform is not hearing the singularity, they are hearing the exterior spacetime settle. An astronomer measuring a ring diameter is not seeing the horizon, they are measuring light bent around it. The distinction is the discipline. If the event horizon could speak through observations, it would speak in negatives: no returning light, no hard surface emission, no escaping signal, no stable outward path after crossing. But around those negatives, there are positives: orbits, rings, waves, jets, disks, flares, and lensing. Black hole science is built by reading both what appears and what fails to appear. The failure to see a surface is especially important. If the compact object had a material surface just outside where the horizon should be, infalling matter might strike it and produce observable radiation. Searches for such signatures in some systems have not found the expected bright surfaces. This supports the idea that the objects possess horizons. It does not solve quantum gravity, but it strengthens the classical black hole picture. The horizon also shapes the fate of radiation emitted near it. Light climbing out loses energy to gravitational redshift. Time dilation affects the rate at which processes appear to unfold. The disk's inner regions move at relativistic speeds, causing Doppler boosting on the approaching side and dimming on the receding side. These effects combine to make asymmetric rings and broadened spectral lines. The appearance is a measurement of motion and geometry. In the EAT image, one side of the ring is brighter, partly because material moving toward us is boosted. The exact interpretation depends on the flow model, but the basic idea is familiar from relativity. Motion changes observed brightness and frequency. Around a black hole, motion and gravity are both extreme enough to draw themselves into the image. The ring is not just a shape, it is a coded record of plasma moving through curved spacetime. Spectral lines near black holes can also be stretched and skewed. Iron emission from the inner disk, for example, can be broadened by Doppler shifts, gravitational redshift, and light bending. X-ray astronomers use these profiles to study strong gravity and disk structure. The measurements are difficult, and models matter, but they provide another way to approach the horizon without crossing it. Timing offers another path. Rapid variations in X-ray binaries can reveal the scale of the emitting region, because small regions can change quickly. Quasi-periodic oscillations may relate to disk motion, precession, or other processes near compact objects. The interpretation remains complex, but timing adds information that images alone cannot provide. Around black holes, time itself becomes an observable instrument. Every method stops at the same boundary. Imaging, spectra, timing, orbits, lensing, and gravitational waves all speak from outside. They can test the black hole's exterior and the behavior of matter near the edge. They can constrain alternatives and reveal environments. But they do not carry a direct report from beyond. The event horizon is successful because it denies exactly that. This denial is not emptiness. Inside the horizon, according to classical relativity, space-time continues for the infalling object until the singularity. Events occur. Proper time passes. Tidal forces act. The fact that these events cannot be shared outside does not make them unreal. It makes them inaccessible to external confirmation. Physics can describe them through theory, while recognizing the absence of direct evidence. In ordinary life, if something cannot be observed, we may doubt its relevance. In black hole physics, the unobservable interior affects theoretical consistency. The information paradox, singularity problem, and thermodynamic behavior all depend on what the horizon means. Even if no telescope sees inside, the interior presses on the foundations of physics. It is hidden from observation but not from thought. A final theory may change the language. Perhaps singularity will be replaced by transition, bounce, quantum core, or something not yet named. Perhaps the interior will not have a classical spacetime description at all near the end. Whatever the answer, it must reduce to the smooth horizon and strong field exterior already supported by data. The unknown cannot be detached from the known. Another way to approach the interior is through a Penrose diagram, a compact map of causality rather than distance. In these diagrams, light always travels at 45 degrees, while the entire infinite outside universe can be drawn on a finite page. They are not pictures of what space would look like. They are maps of what can influence what. For black holes, the diagram makes the horizon's meaning unusually clear. Outside, some light rays reach distant infinity. Inside, even the outward pointing rays strike the future singular boundary. The power of such a diagram is that it removes unnecessary decoration. No glowing disk is required. No star field is required. The question becomes purely causal. Can a signal from this event reach the outside universe? Before the horizon, yes, if it is aimed properly, and has a future-directed path outward. After the horizon, no. The answer changes, because the event lies in a different causal region. That is what the horizon marks. A Penrose diagram also shows why the singularity in the simple black hole is not merely a dot at the middle of a sphere. It is drawn as a future boundary for everything inside. All time-like paths inside end there. This does not mean the drawing proves what quantum gravity will do, but it shows what classical relativity says with unusual economy. The picture is abstract, but the conclusion is physical. After crossing, there is no world line that returns. If the black hole forms by collapse rather than existing forever, the diagram changes. There is no past white hole in the realistic case. There is a star collapsing, a horizon forming, and a singular boundary in the future. This matters because many textbook diagrams of eternal black holes contain regions that do not describe ordinary astrophysical formation. A real black hole is made in time. Its horizon emerges from collapse, not from an eternal mathematical background. White holes appear in the maximally extended mathematical solution of a non-rotating black hole, but they are not observed astrophysical objects. They represent a time-reversed black hole, a region from which things can emerge but nothing can enter. The equations allow the extension, but nature does not seem to produce such regions in the same way it produces collapsed stars. This is another example of why mathematical possibility and physical expectation have to be separated. The same caution applies to diagrams that show bridges between universes. The Einstein-Rosen bridge in the eternal solution is not a traversable tunnel for ordinary travelers. It pinches off too quickly, and realistic black holes formed by collapse do not provide that passage. Popular images often keep the bridge and forget the limitations. The more careful reading is less sensational and more useful. The astrophysical horizon is a one-way boundary, not a confirmed gateway. For an object falling through a forming horizon, the interior may contain the matter of the original star collapsing ahead of it. If the black hole is old and accreting, it may contain infalling radiation and matter from many earlier events. But contained is not quite the ordinary word, because interior volume and simultaneity depend on how space-time is sliced. What the outside calls the black hole at one time does not translate into a simple warehouse of material inside. Relativity makes simultaneity flexible. There is no universal now that cuts cleanly through the outside universe and the black hole interior in the way everyday thinking expects. Different coordinate choices can assign different interior volumes to the same black hole. This does not make the black hole unreal. It means the interior is not a normal container whose contents can be listed from outside at a single absolute moment. This is one reason black hole entropy is so striking. The information capacity seems connected to the horizon area, not to a straightforward interior volume. If interior volume can be sliced in different ways, area becomes the more stable quantity. The horizon becomes the surface on which thermodynamic accounting is performed, even though it is not made of material. That fact continues to influence modern attempts to connect gravity with quantum information. When matter falls in, the outside description eventually treats the black hole as slightly heavier or differently spinning. The detailed arrangement of atoms no longer matters to the exterior field. But quantum mechanics insists that details cannot simply be deleted from the complete state of the universe. This is the pressure behind the information paradox. It is not only about what a falling observer sees, it is about whether the laws of physics preserve distinctions. In everyday life, burning a book seems to destroy information, but in principle the information is hidden in smoke, ash, heat, and radiation correlations. It becomes impractical to recover, not fundamentally gone. Hawking's original argument suggested that black hole evaporation might be different, turning many possible initial states into the same featureless thermal radiation. If true, that would be a deeper loss than ordinary burning. The paradox asks whether black holes really do that. Modern work increasingly suggests that the full process may preserve information, but the mechanism remains subtle. If radiation carries information out, it must do so without allowing ordinary messages to escape from inside the horizon in the simple way. The solution cannot just be a hidden radio transmitter at the edge. It has to reconcile causality, entanglement, geometry, and the smoothness or modification of the horizon. That is why the problem has lasted for decades. For a practical fall into a large black hole, none of these theoretical debates would feel like a rescue. The falling object would not wait for Hawking radiation to return its information in any useful sense. Evaporation times are immense. The local trajectory still moves inward. The information paradox is about fundamental consistency across the black hole's lifetime, not about survival, communication, or escape for the object that crosses. The black hole's lifetime itself depends strongly on mass. A small hypothetical black hole could evaporate rapidly. A stellar mass black hole would last for a span so huge that the current age of the universe is almost nothing beside it. A supermassive black hole lasts even longer. These timescales place Hawking radiation outside ordinary astronomical change for known large black holes, but not outside theoretical importance. If the universe continues expanding and cooling, black holes may one day be among the last compact objects remaining. Long after star formation ends, long after white dwarfs cool, long after galaxies become dark collections of remnants, black holes would still persist. Their eventual evaporation would be part of a future almost impossible to picture in human terms. The same horizon that hides interiors today may dominate the thermodynamics of the far future. That far future is not necessary for understanding a present horizon, but it helps show the range of the problem. A black hole is not just a collapsed star. It is an object where gravity, thermodynamics, quantum theory, and cosmic time meet. The event horizon is the common surface in all those discussions. It is a boundary for escape, a carrier of entropy, a source of temperature in quantum theory, and a test for information. For black holes with charge, the equations allow additional structure, but astrophysical black holes are expected to be nearly neutral. Any large net charge would attract opposite charges from surrounding plasma and be quickly reduced. This is why mass and spin are the parameters that matter most in astronomy. Charge remains important in theoretical solutions, but not usually in realistic cosmic black hole descriptions. Spin, by contrast, is unavoidable. Stars rotate. Gas disks carry angular momentum. Mergers deliver spin in complicated directions. A black hole's spin can affect disk efficiency, jet production, and the spacetime near the horizon. Measuring spin is difficult because observations must be interpreted through models. But spin is not optional. Real black holes are expected to be Kerr-like rather than perfectly static Schwarzschild objects. A rotating horizon has an angular velocity. Near it, spacetime is dragged around. Inside the ergosphere outside the horizon, no object can remain stationary relative to distant observers. This does not mean everything must fall in immediately, because the ergosphere is outside the event horizon. Particles can still escape from it under the right conditions. The distinction between ergosphere and horizon is one of the important details lost in simpler descriptions. Energy extraction from rotation is possible in principle through the Penrose process, and in astrophysical plasmas through electromagnetic mechanisms related to black hole spin. When a jet carries energy away from a galactic nucleus, some of that energy may ultimately come from accretion, spin, or both. Observations show the jets. Theory and simulations work to identify the engine. The horizon is not a material nozzle, but the rotating spacetime around it helps set the conditions. Inside a rotating black hole, ideal mathematics allows regions where the coordinate roles become more complicated. But the inner horizon may be violently unstable due to incoming and outgoing radiation streams. Tiny perturbations can be enormously blue-shifted. This suggests that the neat inner structure of the ideal Kerr solution may not survive in realistic conditions. The phrase "beyond the horizon" must therefore be answered differently for ideal diagrams and for physical black holes. The safest physical picture is not that the interior is simple, but that it is not accessible. General relativity gives strong guidance. Perturbations and quantum effects warn against overconfidence. Observations test the outside and increasingly the near-horizon region. The deepest interior remains a research problem. This is not a gap to hide fantasy in. It is a precise technical frontier. A falling object might also encounter radiation that crossed the horizon after it, but can still meet it inside. The interior causal structure allows some surprising meetings of signals that both remain trapped. For the infaller, the environment can become increasingly energetic. Near inner horizons in rotating or charged ideal solutions, blue shift effects may become severe. These issues show that the interior is not just empty darkness after the crossing. Even an isolated black hole is not entirely isolated in a quantum universe. Fields have vacuum fluctuations. The cosmic microwave background falls in. Distant starlight can cross. Over long enough times, the black hole interacts with its environment. The perfectly empty eternal solution is an idealization. Idealizations are essential for understanding. But real black holes live in a universe with matter, radiation, and history. The cosmic microwave background itself is ancient light from the early universe, now cooled to microwaves. Black holes absorb some of it. For now, this background is warmer than the Hawking temperature of large black holes, so they gain more energy from it than they lose through evaporation. Only when the universe cools further will the balance change. Even the fate of a black hole is tied to the temperature of the cosmos around it. The large-scale universe also shapes black hole mergers. Galaxies collide. Their central black holes sink toward the merged center through interactions with stars and gas. Eventually they may form binaries, and if enough angular momentum is removed, merge through gravitational radiation. The process can take enormous times and depends on the environment. A horizon-scale event may begin with galaxy-scale dynamics hundreds of millions of years earlier. When two galaxies merge, stars mostly pass by one another because the distances between them are large. Gas clouds collide, compress, and form stars. Central black holes may become active if gas is driven inward. The final black hole merger, if it occurs, releases gravitational waves that cross the universe. The event horizon at the center of the story is small compared with the galactic choreography that feeds it. In dense stellar environments, smaller black holes can also find partners. Repeated encounters can form binaries, harden them, and produce mergers. Some remnants may stay in the cluster and merge again, making heavier black holes. Gravitational wave catalogs may contain hints of these different formation channels. The masses and spins are clues. Black holes have biographies, even if their settled horizons hide most individual details. The biography of a black hole ends at the horizon only for the matter that falls in. Outside, its story continues through influence. A central black hole can clear or heat gas. A stellar black hole can reshape a companion star's evolution. A merger remnant can recoil if gravitational waves are emitted asymmetrically. In some cases, a black hole may be kicked from a galactic center or cluster. Horizons are hidden, but their owners move through the universe. Recoils show that black holes obey conservation laws. They are not exempt from physics. If gravitational waves carry more momentum in one direction, the remnant moves the other way. Simulations predict such kicks, and observations search for displaced active nuclei. This is a reminder that black holes are not supernatural exceptions. They are physical systems, often extreme, always constrained by the same demand that energy and momentum be accounted for. The more physical black holes become, the less useful it is to treat them only as symbols. They have masses, environments, formation channels, electromagnetic signatures, and gravitational wave signatures. The event horizon is strange, but it belongs to a real object in a real galaxy. The mystery is not diminished by that realism. It becomes sharper, because the object can be measured. What happens beyond the event horizon is therefore one of the rare questions where the answer is both known and unknown. Known, because general relativity gives a clear causal structure and has passed every exterior test so far. Unknown, because the central endpoint and complete quantum description are not settled. The horizon sits between these truths. It is the best understood edge of the least accessible region. A viewer might ask whether falling in would reveal the answer personally. In one sense, it would reveal a local experience, at least until destruction. In the only sense that matters for science, it would not, because the observations could not be returned. Knowledge requires communication. Crossing the horizon turns experience into a private world line. It is an experiment whose results cannot be published to the outside universe. That final limitation may be the most humbling part. The universe allows us to infer black holes, image their shadows, hear their mergers, and measure their surroundings. It does not allow a report from within. Every answer about the interior is filtered through theory. The best theories are disciplined by outside evidence, but the boundary remains. There are places where even light cannot bring back the news. Still, the outside evidence is extraordinary. The path of S2 around Sagittarius A star. The ring around M87. The chirp of GW150914. The X-ray flares from binaries. The radio jets from active galaxies. The tidal flare from a torn star. Each is a piece of the same larger statement. Black holes are not only mathematical, they are part of the working universe. A black hole's reality does not depend on seeing its interior. We do not see Earth's core directly either, yet seismic waves, gravity, magnetism, and laboratory physics tell us much. The difference is that Earth's core can send signals through the planet, while a black hole interior cannot send signals through the horizon. The comparison shows both the strength and the limit of inference. Some hidden places communicate indirectly. This one does not communicate outward at all. The black hole offers gravity without a surface, darkness without emptiness, simplicity without innocence. It can be weighed and timed. It can merge and ring. It can feed and launch jets. It can hide the details of everything that enters. Beyond the event horizon, the universe continues according to laws we partly know and partly still seek. The boundary does not end physics. It ends return. There is a temptation to answer the title with a single sentence. You cross, you cannot return, and you are eventually destroyed. That is broadly true in the classical picture, but it misses the depth. The crossing may be locally quiet. The destruction may occur later. The final singularity may be a sign of incomplete theory. The outside observer never sees the crossing in the same way. The black hole's environment may dominate the practical experience before any of that. The more accurate answer is slower. A black hole is a region where gravity has reshaped causality. The event horizon is the boundary of no return. Beyond it, local physics continues for a falling observer, but every future path moves inward. Tidal forces grow. Classical relativity predicts an endpoint where curvature becomes singular. Quantum gravity is expected to alter the deepest description, but the confirmed replacement is not yet known. That answer is not less cinematic, it is more precise. A blurred ring reconstructed from radio data. A star orbiting an unseen mass. A chirp in 2 interferometers. A flare from a torn star. A jet crossing a galaxy. These are the real images. They point not to a fantasy door, but to a physical boundary that divides the observable universe from a region whose future cannot be returned. The final horizon of a black hole is also a mirror for the limits of knowledge. Not a mystical mirror, but an operational one. It shows where instruments end. It shows where mathematics must carry the story. It shows where mathematics itself begins to signal incompleteness. The universe is not saying that anything may happen. It is saying that some answers require a theory we do not yet possess. On a telescope monitor, the black hole shadow remains a dark center surrounded by light that survived. Every pixel belongs to a photon that escaped, a calculation that converged, a baseline that measured, a model that was tested. The darkness belongs to paths that did not return. The image is both a triumph and a boundary. We have seen the edge of the place where seeing ends. A final measurement may come from patience rather than spectacle. The next sharper image, the next longer gravitational wave catalog, the next flare caught early, the next star tracked around the galactic center, each one narrows the field of possible answers. None will send a camera through the horizon and back. But each will make the boundary more real, more constrained, and more difficult for careless ideas to escape completely. A radio dish under a cold sky does not know what crosses the horizon tonight. It collects what can still travel outward: the plasma glow, the jet emission, the background source bent by gravity, the flicker from a flare. Somewhere beyond those signals, matter may continue inward along futures that cannot reach the dish. The instrument records the accessible universe, and the black hole defines where access stops. The same is true for gravitational wave detectors lying quietly in their long tunnels. They do not hear the interior. They measure space-time outside as black holes approach and merge. The signal passes through Earth and is gone. From that passing strain, scientists infer masses, spins, distances, and a final horizon. The wave is a trace from the edge of a region that keeps its deepest events from the rest of the universe. If a black hole could be approached without danger, the final lesson would not be spectacle. It would be the narrowing of futures. Outside, choices still include return. At the boundary, return disappears. Inside, every possible future belongs to the black hole. That is what really changes. Not a visible wall. Not a flash. A causal door closing behind an object that may not notice until the consequences become unavoidable. The universe contains many boundaries, but few are this strict. A planet's surface can be landed on. A star's photosphere can be studied through escaping light. A galaxy's edge can be crossed by a wandering star. The event horizon is different because it is made from the structure of possible signals. It is a place where the universe stops sharing what happens next. In the end, black holes are not holes in the sense of empty gaps. They are concentrations of mass energy that curve spacetime into one-way regions. They can be born from dying stars, grow in galactic centers, merge across cosmic time, and shape their surroundings through accretion and jets. Their interiors remain hidden, but their effects are written across the sky in light, motion, and gravitational waves. Beyond the event horizon, the best classical answer is severe and clear. The fall continues. Escape is impossible. Tidal forces rise. The future leads inward. At the deepest point, the equations of general relativity reach a singular boundary where they can no longer be the full story. The best modern answer adds humility. Quantum gravity must complete the account, and we do not yet know exactly how. The last frame can return to the M87 ring, not because it shows everything, but because it shows the limit honestly. A circle of hot plasma, a central darkness, light bent by gravity before crossing the long distance to Earth. Around the dark region, the universe remains visible. Inside it, paths continue where no telescope can follow. The image sits on a monitor, quiet, measured, and incomplete. Somewhere in the Milky Way, an unseen stellar black hole may be moving through a field of stars without a disk, without a flare, without a name. Somewhere in a distant galaxy, gas may be spiraling toward a supermassive horizon and lighting a quasar that future astronomers will measure as ancient light. Somewhere two black holes may already have merged, their gravitational waves still crossing the space between galaxies on the way to detectors not yet built. The event horizon is the line all of these objects share. It is not painted in space, but it is real in the paths that light cannot take. It does not announce itself locally in every case, but it changes the future absolutely. It turns a region of the universe into a one-way passage for matter, energy, and information. Around it, physics is visible. Beyond it, physics continues into a silence, enforced not by emptiness, but by causality. A telescope mirror keeps collecting light. A radio array keeps measuring wavefronts. A detector waits for the next faint strain. The black holes remain where they are, some bright with infalling gas, some dark among ordinary stars, some growing at the centers of galaxies. Their horizons do not glow, but they shape what can be known. And just outside them, the universe leaves enough evidence for us to understand the edge, even if the deepest interior remains beyond the reach of every returning signal.